everyone, welcome back to 3 Deviations. In today's video, we want to cover the quadric surfaces. Now, we've covered planes, so those were really multivariable equation or multivariable ideas or 3D objects of degree 1, right? We had degree 1, so we had x's, y's, and z's. Now we are going to bring that up to one level, so we're going to talk about equations of degree 2 today. This is going to be a lot of theory. We're not going to be using these quadric surfaces as much as we normally would, or, well, really as much throughout this course, but it's still important that we understand them and their connection to 3D space, and it gives us a good idea as to what these objects look like and how to sketch things in 3D space. So in single variable calculus or in single variable arithmetic or algebra, you would cover graphs as either lines, or you would also cover the conic sections. Now the conic sections are the ellipse, the parabola, the hyperbola, and the circle. Now the parabola is a degenerate case between the hyperbola and the ellipse, and the circle is a degenerate case of the ellipse, where the semi-major and semi-minor axes are equal to one another. So now we are going to bring this idea up one dimension, and we are going to cover the quadric surfaces. Now these are basically the conic sections of the three-dimensional world. So let's get started. I'm going to show you just the big equation, the big general equation. So we have a 3D analog to conic sections. Now, the equation that governs this is quite freaky, but that's okay. This equation is ax squared plus by squared plus cz squared plus dxy plus eyz plus fzx plus gx plus hy plus iz plus j equals 0, right? So you've got squared terms, cross terms, and single degree terms, and then a single constant. Now, we can really transform these into far more simple equations that we'll be using mostly, which is ax squared plus by squared plus cz squared plus j equals 0, and ax squared plus by squared plus iz equals 0. Pretty much all of our quadric surfaces cover these two equations, and they will be variations of these two equations. The first quadric surface that we want to cover is the ellipsoid. Now, the ellipsoid is a quadric surface that is in the shape of an ellipse. It looks kind of like a blimp or an egg, however you want to put it. The equation for the ellipsoid is x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. Now, this should be a natural generalization of the equation for an ellipse in the two-dimensional case. Now, in order to graph these, it's often helpful to look at level curves or look at traces. Now, looking at a trace means I'm going to take one axis. I'm going to take one axis, and I am going to look at two axes, pretty much, and I am going to see. what this. I'm going to see what this thing looks like. If I take a little slice, I'll see what it looks like. It might look something like an ellipse of some sort. So if I take a cross-section of this, I will get an ellipse if I take that cross-section. So essentially, if we take a cross-section anyway of this ellipsoid, we will end up with an ellipse, which should make sense. Now, we also have the elliptic paraboloid. The elliptic paraboloid is a parabolic shape, but it could look kind of like a parabola, but in the 3D case. Now, of course, in the degenerate case, where we have a circle instead of an ellipse as one of the cross sections, look more like this. But nonetheless, it would still be an elliptic paraboloid, maybe just a circular paraboloid as the degenerate case. The equation for the elliptic paraboloid is z over c equals x squared over a squared plus y squared over b squared. If we take horizontal cross sections, then we will get ellipses. If we take a vertical trace, we will get a parabola. So if I take my my trace along the z-axis such that I get an xy picture. So if this is my x-axis and this is my y-axis, I will get an ellipse. Then if I take something, if I take, say, the xz or the yz, I will get a parabola. Next, we want to cover the hyperbolic paraboloid. So this is when we have a more hyperbolic shape. In this case, we have the equation z over c equals x squared over a squared minus y squared over b squared. Now, the horizontal traces will be hyperbolas. So this means that if I take an cross-section that is in the xy picture, then I will have a hyperbola. And if I have a vertical trace, then I will get a parabola. Okay, now this should be fairly self-explanatory. Then we also have a cone. Now the cone is the object from which our conic sections are defined in 2 dimensions. Anyways, the equation for the cone is z squared over c squared equals x squared over a squared plus y squared over b squared. If I take a horizontal trace, then I will get an ellipse, and if I take a vertical trace, then I will get a hyperbola. Obviously, there are some caveats about where the cone would be defined and where we would have the correct traces. Finally, we have 2 more. The first is the one-sheet hyperboloid. One-sheet hyperboloid kind of looks like a nuclear smokestack or something that they have at the plants. That's actually how they design it. Anyways, we define the one-sheet hyperboloid by x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Now, we will have horizontal traces of ellipses and vertical traces of hyperbolas. Finally, we have the two-sheet hyperbola. Now, this is the other hyperboloid that we can have. It shouldn't be hyperbola, it's hyperboloid. Anyways, if we get the two-sheet hyperboloid, equation for that is negative x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. Now, if I have a two-sheet hyperboloid, I will have horizontal traces that are ellipses. I will have vertical traces that are hyperbolas. Obviously, again, caveats about where it's defined. So those are the quadric surfaces. I hope that this video is helpful. Using these equations is fairly easy, so I won't go over too much about them. They will come across in a later video. In the next video, we're going to introduce vector functions in our next unit, Unit 2 of Multivariable Calculus. That is the 3rd of our prerequisite unit, and then we will be ready to move on into partial derivatives, multiple integrals, and vector calculus. Thanks for watching, and we'll see you next one. Bye.